Welcome to Moments of Momentum, where we highlight historic AI trends. Today, I want to talk about a topic that is near and dear to my heart, NLP, or natural language processing. Ever since I was young, I was fascinated with the problem of language, and it's always been the primary lens that I use to view AI. Now, people use NLP in a lot of different ways. They'll also throw out terms like NLG, that's natural language generation, and NLU, that's natural language understanding. Now, some people will assert that these are three mutually exclusive categories, but that doesn't really reflect modern systems where they bleed into each other pretty significantly. Now, we're going to be using NLP in a very broad sense, which is to say anything where AI and text intersect. Now, this is the broadest sense of the term, but it's also the most consistent. And frankly, this entire space is a hot mess when it comes to terminology. Now, before we start, there's two things that I want to say. The first is that there is another NLP that stands for neuro-linguistic programming. We are not talking about that. That's a kind of pseudoscientific mumbo jumbo. The second is that this is a whirlwind introduction to a century of research and thousands of PhDs. So obviously, if I get anything wrong, I expect to get blasted in the comments. Now, let's roll back the clock. Let's go back to the 1950s to that same hoity-toity MIT convention that we were talking about last time. In a neat little bit of history, I actually managed to find an invitation to the original event, which I've linked down below. Now, I want to take some time to paint a little bit of context around this, exactly what the hype was that led to this symposium. Now, back in the 1950s, the big thing was computers. The same way that the dot-com boom was all about the internet and interneting all the things, even things that didn't make sense, the 1950s big boom was around computers and computering all the things, even if that didn't make sense. So when we talk about the 1950s, we're really talking about very early NLP that's relying on primitive basic programming, really if-else statements. And we're also talking about the start of computational linguistics, which is really just the notion that you can look at language in a computational way, which was very novel. And this leads us directly to the first generation of NLP, the expert system, built on the back of these if-else statements and what we would think of today as very basic string processing and programming, is something that was revolutionary at the time. And back then, when all they had was the hammer of simple programming, everything started to look like a nail. And before long, they believed they could solve all of language and indeed all of human intelligence with the application of these rules. And now they didn't do this willy-nilly. They had a very detailed procedural way for exploring the way that they would create these rules. So this whole generation of AI is built on the back of something called the physical symbol system hypothesis. I'll probably do a whole video about that someday, but the most important thing to understand about it for now is it's built on this notion that words are atomic things. They are discrete symbols that represent things in the physical world that then are composed in these atomic ways. So when you look at these systems, they're very explicitly around creating connections between words and codifying the way that words relate to one another. Now, to give you a sense of just how crazy this got, I'm using an example that's actually from a little bit later than this first generation called Wordnet. Now, Wordnet was first released in the 80s, and the latest release was in 2011. It's no longer actively developed, but I think it's a really good example of the kinds of systems we're talking about, and it's easily accessible, and it's very Googleable, which means I can link to everything I'm about to talk about. As we established, the goal of most of these techniques is to adopt as wide an array of linguistic formalisms as possible. So when we look at Wordnet, you're adopting formalisms like the word dog has exactly 7 definitions, and 6 of those definitions are nouns, and 1 of those definitions is a verb. You say each of those definitions is centered around a cluster of synonyms, and that's where things start to get really interesting. Now, most people are familiar with synonyms and definitions, but these terms are used a little bit differently in computational linguistics. In computational linguistics, each one of these distinct definitions is called a word sense. Classic example, a mouse has 2 very obvious senses, a computer mouse and the animal mouse. Those are 2 different word senses, just like there are 7 explicit senses of the word dog. And similarly, most of us have heard of synonyms. And in Wordnet, each one of these word senses has a group of mutually equal synonyms called a synset, which is a collection of words that all approximately mean the same thing. And that's where things really start to get interesting, because most of Wordnet is these connections between synsets, saying how do these relationships relate to each other? And that's where you start getting beyond the synonyms that we're familiar with. You've got hyponyms, you've got meronyms, you've got holonyms, both member and part holonyms, obviously. You've got hypernyms, which can be both direct and indirect. You've got sister terms, and just in case that didn't cover everything, you've got derivationally related terms. And by the way, that's just for the noun senses. When you move on to verbs and adjectives and all of the other parts of speech, you have an explosion in other types of relationships. So the goal here is formalism. Once you create all the rules between all the symbols and all the words, then you'll have totally understood language. That's the idea. And to their credit, these systems worked very well in highly constrained, unchanging environments. And that leads us to the two real issues that led to the downfall of the expert system. Unfortunately, expert systems suffer from two really key drawbacks that really limit their applicability. One is theoretical and one is practical. The practical one first, which is the incredible expense of building out these ontologies. It takes a tremendous amount of effort, measured in person centuries, to build one of these rule systems out. When you look at something like Wordnet, the definition for dog is 10 pages long and doesn't even include doggo, pupper, or doge. Which leads us to the second issue. Dictionaries are fundamentally history books. As soon as you finish creating one of these systems, it's out of date. And that means it's not just incredibly time-consuming and expensive to create these systems, but it's an ongoing cost that's intensely expensive to maintain on into the future as well. So let's fast forward a decade from that original MIT symposium to the mid-60s. And that brings us to the ALPAC report. And the ALPAC report was one of several attempts over the years to understand really why AI wasn't having the kind of success people expected it to. The ALPAC report is civil, but absolutely withering. I wanted to read you a couple of quotes just to explain how intense this paper is and cut through some of the academic jargon to explain to you really what they're saying. The first sentence: "We quickly found that you were correct in stating that there are many strongly held but often conflicting opinions about the promise of machine translation and about what the most fruitful steps are that should be taken now." Translation: everybody is angry and nobody agrees. The second quote: "Therefore, among the important kinds of research that need to be done and should be supported are: 1. Basic developmental research in computer methods for handling language as tools to help the linguistic scientist discover and state his generalizations." Now, of course, his generalizations, they say. And as tools to help check proposed generalizations against data. And 2, developmental research in methods to allow linguistic scientists to use computers to state in detail the complex kinds of theories, for example, grammars and theories of meaning, they produce, so that the theories can be checked in detail. Translation: you'll need to go back to basics and learn how to check your work. Between the two of these, the ALPAC report paints a picture of scientists that have lost their way, that have thrown the scientific method by the wayside, and it was destructive to the field. And these critiques are correct. And the ALPAC report is very long and nuanced and makes a lot of good points. But believe it or not, neither of these 2 points was actually the key reason that the ALPAC report highlighted for the lack of success in machine translation. Believe it or not, the main issue in the 60s was compute power. Now, if you're a computer scientist, you might be surprised by that. Expert systems are generally believed to be the most compute efficient methods out there. And today, in a modern computing cycle, you think that the if-else statements and these string processing operations are essentially free. And today, you're correct. And in fact, that's a very key point. Both of the next 2 generations of NLP technology that would be developed already existed at the time. Firth was talking about the distributional hypothesis in the 50s, and Rosenblatt was pitching the perceptron, which would go on to become the neural net, in the 60s. The problem is that at the time, neither of those 2 techniques had anywhere close to the amount of compute power that would make them feasible to really experiment with in a real scale. Now, both of those techniques were wildly beyond the capabilities of computers in those days. Expert systems could actually be built, if just barely. Unfortunately, in practice, these systems were slower, more expensive to run, and less accurate than human translators. The closest thing to a compliment I could find in the ALPAC report was saying that at least these endeavors have cost less than the particle accelerators in other fields. Now, as soon as the LPAC report came out, the National Research Council, who had bankrolled this whole thing, lost their whole damn shit. At that point, in 2020 dollars, they had poured in about $750 million to this effort. And after the report came out, they canceled it. They cut all ties, they fired people, they ended careers. They said, we're done here. That was the beginning of the end. Expert systems still exist today. In fact, they're still quite common because they're so easy to build, but they languished. They haven't really advanced since the 50s. They're still limited in these fundamental ways that more compute won't really solve. And after a long series of other reports, this led to the first AI winter. And in academia, at least, it really marks the end of expert systems as a trendy new topic of research. Next time, we'll talk about the next generation and the distributional hypothesis, which underpins that next class of NLP algorithms.